All right, here's 5-2, day 1. First of 3. Kind of a similar approach that we took with 5-1, with splitting it up over those 3 days. Only difference here in 2, we turn our attention over to logarithms, which might, we might have a little bit more to talk about in these days, as that concept is a little bit less familiar. But let's turn our attention to this graph. It's 2 to the x power. So actually, let me do this first. Because logarithms can have kind of this kind of weird element at first, like, okay, what are they? The inverse of an exponential function is a logarithmic function. So we've touched on inverses before, right? And that's a good way to start thinking about logarithms. So if we're going to take like this inverse approach, then the right place to start is with an exponential function like 2 to the x. Okay? So let's whip out a little table for it. You've already got the graph there, and I think somewhere along the way in 5.1, with a table of values, I think we produced a sketch of it. Okay. Your y values would be, let's see here, we'll start over with the positives. 2 squared is 4, 2 to the first is 2, 0 power is 1, 1/2, 1/4, and 1/8. There we go. Okay. So there we've got a table and a graph, all right, for 2 to the x power. And now let's do this. We've done this before. This isn't a kind of a new trick or anything. Let's switch x and y. Okay, switch x and y. So I don't want to write the table again, right? So you just know that I'm going backwards here as I put these points to produce the graph. So for my first, I'd say x is 1/8, and then y is -3. Okay, I'm going to zoom into my graph here a little bit, just so that's a little easier. I know zoomed up that close, it's probably a little blurry for you, so sorry about that. Let's see here, go over 1/4 and then down 2, over 1/2, down 1. Go through the point 1, 0, 2 over, 1 up, 4 over, 2 up. Okay? Again, this came up in day 1, same situation, recording at home. Scout's with me again. If you can't hear him in the background, I'd be stunned. This guy is, it's intense, because the 5-1 videos, I recorded him yesterday. This is literally, this is Scout's life as a 12-year-old dog. He goes to his bed here in the office and he just snores his brains out every day. It's like, he's living his best life. That's all I can say. That's what he's doing. All right, back to reality over here. We've got 2 to the x, and now we have log base 2 as well. Okay, now these are inverses, right? And here's another thing I want to show you. This is just kind of approximate here, but that would be the line, a little squiggle in the middle there. That's the line y equals x, because remember, when you're talking inverses, it's a reflection over the line y equals x. This is no exception, okay? So logarithmic graphs are the inverse of an exponent, okay? That's what they are. If you wanted to see how the algebra would work, okay, to write the equation, switch x and y, then this part's a little bit weird, but a logarithm is also like an operation. Okay, we're going to see that on the next slide that we'll evaluate some logs. Okay, but take log base 2 on both sides, and this would give you the equation, right? For the most part, we're not going to go super far with the algebra of logarithms, more the graphs, but this is the same deal with getting an inverse. Okay, switch x and y, right? And then we'll take log base 2. And this is where you really have to think about a log as an operation. Okay, its graph is the inverse of an exponent, and as an operation, it's also the inverse of an exponent. So over here, those cancel. And then you get log base 2 of x equals y. And that's the graph that we have in the blue, okay? So that's just kind of our introduction. I think the graphical side of it helps because it gets you thinking along the right lines, right? It's the inverse of an exponent. That is like the way to think of it. So now let's get dialed in on logs here and get into some of the stuff that we should know about them, okay? I think this is just really helpful. Okay, y equals log of a of x. For those two sides to be equal, it's only true if a to the y power equals x. Okay? Couple things here to also note. Let's stick with this. This is no different when we were talking about exponents. A is still the base. It's got to be positive. It can't be 1. That still applies. You'll actually see I think it's in the next day's notes, we get a little pickier. Like a logarithmic graph, A could be between 0 and 1. We really tend to look at ones where A is bigger than 1. So don't be surprised if you see that where we get a little bit pickier and we're like, no, A needs to be greater than 1. Another thing to note, we'll look at this a lot more when we see their graphs. Logarithmic graphs are only defined when x is greater than 0, okay? Highlight or star that point, because we'll come back to that quite a bit, okay? They're only defined for x greater than 0. They have an asymptote that kind of causes that to happen. Last thing for this slide, this part right here, to read this would be read log, I'll put this in quotes here, base A of x, log base A of x. All right, so here I'm going to do some evaluating. I'm going to kind of take two approaches, calculator, no calculator. We'll dabble with both. I'm just going over ones here where I want you to see that I'm going to take the approach of no calculator. Because if the numbers do work out okay, you can evaluate logarithms without a calculator, okay? Easily can be done. Now for each of these, I'm going to write a little more than I need to because, again, my big concern in terms of where you're at with logarithms is just kind of intuitively understanding what they are and what they do, okay? So right off the bat here, on A, what this is asking is, and think of it as a function, right? It's like it's a new function family. It's just an inverse that's built off of exponents. Log base 2 of 32. So it's like the function is log base 2, and we're plugging in the x value of 32, okay? I think this is tremendously helpful to switch it over to an exponent, which you can do if you switch x and y. Okay, you kind of saw it when I was solving to for the inverse. When I switched it over to a logarithm, right? Swap x and y, and then you just kind of switch it from a log to an exponent. That really gets to what this is after. And in fact, I don't want to call that x. This is about specifically when x is 32. That's the question that we're asking. 2 to what power is 32? Okay? I think it's incredibly important to be clear on that when you're dealing with logarithms. That's what we're after. That's the question. Okay? Now, a little bit of guess and check, you could probably figure out at some point that 5. 5 is the number that does the job. 2 to the 5th power would be 32. Okay? So if you were writing that as a function, we saw this. Input of 32, output of 5, right? If we were to make a graph of this, 32 would be an x value. The y value that would go with it would be 5. All right, B. Instead of f of x, I'm just using y, but log, different base here, right? This is, I think, the first one we've seen other than 2, because 2 is a really common base. We'll see some other common ones. 10's another one you'll see a lot. Okay? But remember what the rule said. It just has to be positive and not 1. Okay. Log base 3 of 1, 3 to what power is 1? That's what we're after. What number would make that true? Y would have to be 0. Anything to the 0 power is 1. Again, if you were to think about this as a function, to get the y value of 0, we had to put in the x value of 1. And if you were graphing this, that graph, and we've seen a picture of a logarithmic graph, right? Log base 2, as you would expect, it has kind of the opposite characteristics of an exponential. I mean, we saw one that was the inverse of an exponential growth. That 2 to the x was increasing really slowly and then fast. Logarithmic graphs, as you would think, being the inverse, they do the opposite. They increase really fast, and then they start to slow down. What is your y value if you were taking log base 4 of 2? Or 4 to what power would give you 2? Little guess and check, right? And that's really, as you're seeing these, once you get to this step right here, I would anticipate you might have an obvious one where you can just see the answer right away. Otherwise, you might be left with a little guess and check, okay? Which is no big deal. Again, I'm going to give you some problems where you're probably going to get to it pretty quick. So again, we'd get the y value of 1/2 if we put in the x value of 4. Because again, I keep writing this out because I want you to be thinking of these in terms of functions. You put in 2, it gave you the y value of 1/2. If we were to graph this, it would go through the point 2, 1/2. All right, last one. Here's log of 10. Y equals log base 10 of 1 over 100. Or 10 to what power would be 1 over 100? It's the other way to look at it. Okay? Again, after a little bit of guess and check, you'd see -2. Right? Meaning -2 equals log base 10 of 1 over 100. If you think about solution points that would show up on a graph, if you put in the x value of 1 over 100, which is kind of a weird x value, but that's the one we used here, you would get the y value of -2. All right, there's going to be times you need to use a calculator to to evaluate a logarithm. These would be those calculator cases, right? You'll see we'll do 10 all the time, right? By the way, if the base is 10, keep this in mind. Typically, all you see is that. 10 is so common that if that's the base that you're using, you don't even write 10. You just don't see a base, okay? So know that that's going on. Don't get confused. Nothing went wrong. If you see a problem in the book and it's like log of x, like what do you mean? What do you mean log of x? Log base 10, okay? So these would all be calculator ones. You know, think of these as equaling y. And you can see these would be a lot harder if we approached them the same way. And we're like, okay, hey, 10 to what power is 13? Okay, 10 to what power is 13? That's going to be a hard one to get, right? It's going to be a tricky little one. So that's where you would go here. If you look over on the left side, right, if you have a TI-84, it's all the exponent and logarithmic stuff is kind of together. Okay, so you would just type in that, and you would see okay. $432.12. Okay, again, another one where you're like, all right, 10 to what? But you could take the same approach. You'd have a lot of guess and check to do. You'd have quite a bit to do. Okay, but it could be done. Otherwise, you would just throw that into your calculator. 2.636. Okay. Here's an interesting one, right? Again, the question we're asking here, if this were to equal y, right? Remember, I thought of that one the same way, setting it equal to y. 10 to what power equals negative 19? Remember, if you type that into a calculator, you would get an error, okay? Which remember back up here, right? You put in the x value of negative 19. We'll look at this closer in day 2 when we do graphical stuff. The domain would be x greater than 0, right? So that's not in the domain, so it doesn't work. What it really means is right here. You could look far and wide to try to put a number in for y that you could do 10 to that power to give you negative 19. It's not going to happen. Okay, it's mathematically impossible, which is why this has the restricted domain that it does. Okay. All right, log of 1. (10) to what power is 1 is what you're after. Okay, that's what the question is answering there. That one you probably could have, you wouldn't have needed a calculator here, I don't think, to figure out that it's 0. You probably would have gotten to that pretty quickly. Okay? All right, here's a few properties. Most of them pretty self-explanatory. If you look at kind of what they mean exponentially, like right here, you're usually seeing things that you would say, yeah, I knew that. Anything to the first power is itself. Anything to the 0 power is 1. Right? You saw this one here as well on number 3. When I was solving to get the inverse, I did that I used the logarithmic operation to get the log and the exponential base to cancel. Okay. Then in the next slide, when we're solving here, we'll use the one-to-one property. Okay, shows up with logarithms, really similar to the way it did with exponents. Okay. But if one of those applies, you can simplify it really, really quick and really easy. Okay, like for example, log base 4, right? Because on all of these, it's just saying a, right? Which remember, all we say about a is it really should just be positive. And make sure it's not 1. So right there, I'd see property number 1 is really what is applying. All right, that you're taking the log of 1, and you would know automatically that's got to be 0. Part B is property number 2 that matches, right? The base is 7, and it's of 7. Okay, that would be 1. Right, which again, if you were thinking about that as an exponent, right, you're saying 7 to what power equals 7, which would be 1. Part C, I showed it to you in the opposite way, but property number 3 shows it doesn't matter, right? If you had an exponent of base 12 and a log base 12 in the exponent, they would just cancel. And you would just be left with x. Okay. Again, when I solved for the inverse, I did it in the opposite order. But as you see from property number 3, order doesn't matter. If you have in that same expression an exponent and a log of the same base, they're going to cancel each other out. Right? That's what inverses do. So I guess if you're simplifying or evaluating logs, always keep that list of 4 close, right? They're intended to kind of be shortcuts to help you out, that if you recognize that's what's going on, it's going to be quicker and easier, okay, than even using a calculator. All right, I'm going to head down here and do some solving, okay? Because there's really, with how the one-to-one property shows up, it's not really any different than exponents, where we saw that if you had the same base on both sides, you wanted to rewrite it so it had the same base. Okay, now we're not going to see that happen here, because if you have logs that have different bases on each side, it's a hard case to deal with, right? And again, you saw with exponents in day 1, we managed with it a little, okay? Not a lot, but logs we won't. We'll just be left with this case. And it works out nicely when it happens, that if you have one log on each side and it's the same base, they just cancel. And you get x equals 9. Same thing right here. This one's a really nice one. Get rid of the log base 3's, and you're like, oh, sure. There you go. X would have to be 14 to make that statement true. Log base 4, right? Again, 1 of each. That would leave you with x squared minus 6 is 10. This one ends up giving you a little bit of a quadratic. And you end up getting 16, okay? So it kind of depends on what you have inside the parentheses here. Once the logs cancel, it's like, what do I have left to solve? Well, it depends on what's in there, right? You're typically looking at either linear, maybe quadratic is about all you're gonna have to deal with. Square root and square root. X would be plus or minus 4, kind of a unique case there because you had that quadratic on the inside of the logarithms, right, with the x squared on the left side there. You end up getting 2 solutions, right, because you've seen so far in the first 2. Usually if you're working with logs, you would typically expect to get 1, but C is kind of a unique case where you could end up getting 2. All right, we'll call it quits there for day 1, right? Again, kind of that same approach we had with exponents, where day 1, I took it easy on you and no graphing. Day 2, once again, that'll change. And we're kind of in good shape. We took a little bit of a look at graphing with logarithms. So you've seen one, you saw log base 2, but we'll get back into that, and just, now that we've seen the graph, we'll take it further in day 2.